Okay, in this video, what we need to take a look at is the principles, basic principles of equilibrium. This is a basic chemical feature on reactions that we need to consider for biochemistry, although biochemistry reactions, as we'll see in our subsequent videos, is a bit more complicated. But let's start out with a basic review. So if we consider a reaction where we have two components, say for example A plus B, forming C plus D. A plus B are the reactants in this reaction, and C plus D are the products. I've drawn my arrows both ways because most of these reactions that we'll be talking about in biochemistry, the vast majority, are reversible reactions. The ones that aren't reversible, I will point out to you as we go along. Now, an important consideration is determining which direction this reaction will proceed. Will the reaction proceed from A to B, A and B to C and D, or backwards, C plus D to A plus B? And one of the primary principles needed to be examined is the concept of free energy. Because free energy between the reactants and products, comparing these two, is what's going to determine if this reaction will move to the left or to the right. So if we look at a graph where the y-axis is free energy, our component of G, and these reactants have a particular free energy. Now the free energy of these reactants is dependent on the chemical nature of the reactants. We'll get into this in a second. But let's say that the free energy capacity of A and B, the reactants, is this value up here. Now if we examine the free energy levels of our products, let's say, for example, the total free energy is lower in the products than it is in the reactants. That means that we have a decrease in free energy from A and B to C and D. This is characterized as a negative change because we are reducing our free energy, moving into the right direction here. And this change is considered a negative delta G 0 naught. Now the designation of delta G 0 naught is called standard free energy change. The standard free energy change is an inherent property of the reaction itself. What I mean by inherent to the reaction is that this reaction, because we have a change in the free energy calculations, free energy amounts between reactants and products, this is standard for this particular reaction. If we change our reactants to, say, E and F, leading to G and H, that is a completely different reaction and will have a different delta G 0, standard free energy. So the standard free energy change is the description of the energy change between the reactants and the products. Now the fact that this, the way we've drawn it here, is a negative free energy change, negative free energy change means that this is an exergonic reaction. Recall exergonic reactions give off energy, and these are favorable. And this reaction will proceed to the right because we have a decrease in energy. Now let's look at the reverse of this reaction, where we are going to look at free energy change differently. Now let's say we have a similar type of reaction setup where we have reactants that have a lower free energy. So let's say E plus F. Let's say that our products are G plus H, and these have a higher free energy. This means that in order for this reaction to proceed in the direction from E plus F to G plus H, we are going to have to put energy into the system. This is an endergonic reaction. Hence, our delta G is going to be positive. Now, what this tells you is that the favorable reaction is going to be in the other direction. So the endergonic reaction is unfavorable, but the reverse reaction going from G plus H to E plus F is a decrease in free energy, which means a negative delta G0. So that is the favorable direction, going in this direction. Whereas our first reaction, the favorable direction, is here because of the negative delta G0. Now the next question is how does this reaction, how do we calculate the delta G0s? Well, the delta G0 is the summation of the free energy of each one of the reactants and each one of the products. And we calculate that by looking back on our familiar equation of delta G equals delta H minus T delta S. Now this equation here, this is our enthalpy equation. The enthalpy equation is the energy of the bonds of either E and F, G and H, A and B, or C and D. So this particular value will be the calculation of energy for the bonds of that chemical species. Delta S is entropy. And entropy takes into the consideration of the second law of thermodynamics that in all systems in the universe, reactions tend to head toward the highest level of entropy. But entropy is a measure of order. So the more ordered a chemical is, the greater the entropy, the less the entropy. So a highly structured molecule will have high order, and we will have a low value for entropy. So how do we use this equation to calculate the free energy of each one of our reactants and products? Well, if we look at, for example, species A, chemical A, we would calculate the formation of these bonds. So if this is a multi-atom molecule, we would calculate the bond energy between the atoms to construct chemical A. Here is our energy of our bonds. If it is a complex molecule, we have to figure in our absolute temperature times our entropy factor. Once we calculate this for this species, the delta G then becomes the standard free energy of this particular molecular species. We could call this delta G prime sub A. We will also do this again for B, for C, and for D. Once we have this, then we are going to calculate the sum of free energy of the products minus the summation of the delta G of each of the reactants and this value that we get here will equal the delta G 0, the standard free energy of this particular reaction. So again, the summation of these delta G calculations for example, C and D as our products, and A and B are reactants. And this gives us the standard free energy defining this particular reaction. Now, we need to consider this, because of our equilibrium discussion, of what is the relation of free energy, standard free energy change, to equilibrium. This is important because we are considering in our chemical reactions chemical species that will have very defined concentrations in these reactions. So the equilibrium, or the concentration of these reactants and products, when we achieve a steady state situation, remember equilibrium is its steady state, which is defined by the forward and reverse reactions being equal, and thus the concentrations of reactants and concentrations of products remain steady. There is no change. We have reached equilibrium. This calculation is very important, connected to the free energy change. The relationship of this can be studied by examining the equilibrium constant, Keq. This is defined as the concentration of C, concentration of D of our products over the concentration of our reactants, A and B. So when we reach equilibrium, the concentration of products over the concentration of the reactants will be a steady number, and that will give us our constant. Now this value here is related to delta G, and we can calculate delta G 0 from this, or we can calculate the equilibrium constant by this equation. Delta G 0 equals negative RT times the log, natural log, of the equilibrium constant. R, of course, is the gas log. T is temperature, so these are constants. So our variable in here is our equilibrium constant. Now if we examine our equilibrium constant, if we have a very high concentration of C and D, of our products, and a low concentration of A and B, our reactants, that means we are going to have a very high equilibrium constant. Let's say this is much greater than 1. The natural log of a number greater than 1 is going to be positive. So we have a positive number here. We have a negative factor in front of RT, which is going to give us a very large negative free energy change. This is indicative of a reaction that is exergonic. Recall what we saw back here, in our calculations of our standard free energy change between our reactants and products that this is an exergonic reaction when we have a negative delta G. When we have a high equilibrium constant, that means that the reaction is going to want to push to the right in favor of forming the products over the reactants. That will give us a negative delta G. In contrast, if we have a small equilibrium constant, let's say much less than 1, the natural log of a number less than 1 is going to be negative. These negatives will cancel each other, and that will give us a positive delta G prime. This, of course, is an endergonic reaction. Now compare this calculation with our endergonic reaction, where here we're going to have, let's say, very little product formed, and this reaction is going to want to stay more in the form of the reactants. That would give us a small equilibrium constant. Let me write this out here. And for this reaction, the products over the reactants, if this number is very small, we have very little product form. So that means we have a delta G that is not 0, that is positive. This is an endergonic reaction moving in this direction. So therefore, the reaction is going to be favorable in the opposite direction, because this would be the negative delta G, which is the inverse of this equilibrium constant, which would be a high equilibrium constant. So these are the basic fundamental principles that we need to recall in equilibrium kinetics. And now what we're going to turn to next is looking at determining delta G free energy changes of biochemical reactions.